Hi, my name is Jeff. Sorry, I'm gonna be coughing the entire time, but ignore that. And I'm doing an introduction on Hamiltonian mechanics, and this really will be an introduction, so there's gonna be a lot of hand waving for some of the more formal stuff that can be done a lot more formally. But just know everything I say can be derived rigorously, but because it's an introduction, I'm just gonna say this is true, do this as an exercise, and so on. So, first thing, where's the marker? There's the marker. Sorry. First things first is, with the history of physics, it started with a dare. One of Newton's colleagues dared him to figure out how the world works. 6 months later, he came back to his friend who dared him and said, "Here you go." And he handed him basically calculus and the foundations of what we would now call physics. That's not to say what Newton did wasn't impressive. What he did was really impressive. It's just kind of cool that he did it on a day. So the most important thing is what he did was this equation. He didn't actually write it like that. He really, there was a little bit of disagreement on how he actually wrote it, even though we could just look at the original paper, or his original work. But a lot of people would say he actually wrote it like this. Something like this, that the integral momentum with respect to time is force. So what I'm going to do, so this is in your introductory physics class. This is what you're taught what modern or classical physics is. Knowing the forces of a particle, and knowing how acceleration is related to the position, that is the second time derivative. That's what the two dots mean. Each dot represents one time derivative. So by knowing this relation, you can then calculate the trajectory of any particle. Well, my goal here today is to get your feet wet with two other methods of how to calculate the trajectories of particles that seem very weird at first, but are actually very useful. So to start, I should also say that this is still equal to p dot. So to start, I'm going to start by defining two quantities. A quantity I'm going to call d, or t, and that is the integral of p dv, and this is v as in your velocity. I'm going to try and just write this as that. So it's the integral of your momentum with respect to your velocity, and v, which is the integral of the negative force with respect to your distance. So most of you probably have never seen this before. This is a definition for potential energy. This is what's commonly used to define potential energy. This only works for a force if it's conservative, i.e. this integral is independent of the path of integration. It's not really common in the one-dimensional case, but in the 2, 3, 4, whatever dimensional case, higher than one you want to do, that can be a problem. But for purposes of this introduction, we're only going to focus on where this is path independent. Okay. So we said this is our potential energy. It turns out, through some manipulations, you can show that this is equivalent to your kinetic energy. So I wrote these in terms of the linear quantities, your linear position, linear velocity, linear momentum, linear force. These definitions would be true if I were to swap this out for angular momentum and angular velocity, your angular torque, or angular force, also known as the torque, and your angular position, more commonly just called your angle, or whatever generalized coordinates you want to come up with, because sometimes knowing how far in the x direction, how far in the y direction you are is not always the easiest way of solving a problem. So these would also work in general. So from these definitions, we can get a couple nice properties really quickly. You can get that the partial derivative of t with respect to our velocity is our momentum. We can get that the partial derivative of our potential energy with respect to position is negative force. However, I'm going to instead write it like this. We have the partial of kinetic with respect to position is 0, and the partial of or potential with respect to velocity is 0. These should be pretty obvious from the definition. These would require a little bit of trying to convince yourself. So as an exercise for the reader, show that these follow from that definition. Okay. So now that we have these quantities, we can rewrite this equation in terms of t, v's, and partial derivatives. So trace this and read my notes. So first things first, this is the time derivative of momentum. So we can write this as, and this is a total derivative, not a partial derivative. I can move everything to this side, and for purposes that'll become apparent later, I'm going to rewrite this as negative the minus of that quantity. That's equal to 0. Now, we can always just add 0 wherever we want and not change the equation. So I'm going to add 0 here and here. So I'll choose to do that like this. So we're subtracting 0, we're adding 0 there. And again, we can add or subtract a 0 and not change our result. But as we saw over here, these are two different ways of representing 0. So let's put those in here. Partial d over partial n. And if you notice, we have the same partial derivatives with respect of t minus v, same partial derivative of t minus v. Using the linearity of the derivative, we can actually rewrite this instead as, and again right here we can rewrite this as, so you notice, that should be d over dt. If you notice, we have this t minus v quantity that just seems to be important. So let's call that, let's give it a name. That is called our Lagrangian. And again, t is our kinetic energy and v is our potential energy. This is a function of, usually it's a function of only your velocities in whatever coordinate system. This is usually a function of your positions in whatever your coordinate system. Okay. So we can so we can rewrite this equation using using this fancy L. So we get d over dt of partial over partial x dot over Lagrangian minus partial over partial x over Lagrangian is equal to 0. Okay. Now, in introductory calculus, you guys probably learned how to minimize and maximize functions. Okay? Well, in higher level math, there's a branch of physics, or a branch of math called calculus of variations. Calculus of variations takes the same idea of optimization, and instead of applying it to functions, we are applying it to functions of functions. So, for example, we have, say there exists alpha, which is a parameterization of some curve in R2. What value of alpha that bounds the largest area for a given length, arc length. Or, what's the other example? Or let alpha be, again, some curve between 2 points. What value of alpha will give us the shortest distance, using some arbitrary definition of distance. Again, those are optimization problems, but you can't really take a derivative and set it equals 0. Actually, you can, you just have to convince yourself that you're not, so a way to do that, for example, just a brief side note. For the distance one, what we would do is we could rewrite distance, or arc length, which I'll call little s. We can rewrite that as so this is a way of calculating arc length using the standard Pythagorean, or what's called the L2 norm, which is equivalent to the Pythagorean theorem for measuring distance. So what we can do is, instead of taking a derivative on alpha, we can do what's called a functional derivative on s, and doing that, we would find that the solution that maximizes, or the value of alpha, which satisfies this equation, also satisfies the following equation. How do I write this? Yeah. So what we can do is, actually, yeah, I know how to write this. D over dt of partial. Okay. So if you notice, we're taking the derivative of the magnitude of this with respect to this. So we're taking the derivative of this function, or of this derivative of a function with respect to its derivative. So basically what this means is we pretend for a moment that this is just a variable, and we're finding the derivative of the length function, or the length of, only that variable. And if we notice, again, pretend alpha prime is just a variable. Well, alpha prime would just be a variable that's independent to the variable alpha, so we would know that this would be 0. So we're just solving this equation. But if you notice, the way I wrote it, this looked extremely similar to this. It turns out the way to maximize an integral is to plug it into an equation of this form, that form. So this is equivalent to saying we want to find we're trying to find the value of alpha, the curve alpha, such that the integral, capital S, which is, let's say, the function of alpha, or alpha dot, or I'm going to rewrite this in terms of the position vector x dot, and t is equal to the integral from a to b of, again, this Lagrangian, which is, again, a function of x dot, and t, dt. So we call this integral, we don't have a fancy name for this integral, but we call this quantity the action. That usually when Lagrangians are first introduced, you start with the action and then you show that the value of x, which maximizes that curve, also satisfies Newton's equation. I did it in the reverse order, that Newton's equations are equivalent to maximizing or minimizing that integral depending on specifics. And usually that's all the actions ever talked about. Maybe you might get one question on a test that says find the action of this system for the specific trajectory, but action will become important at the end of this talk. So before we get into Hamilton, or the next method, we basically started with, we have force, and this one vector equation, F equals ma. This is technically one vector equation, but it's really a system of equations, one for every dimension you're in. We've replaced it. Oh, and also if you have more than one parameter, like you have an x direction, a y direction, or an r direction and a theta direction, you would just apply this for every coordinate. So like you would do like partial y dot y, partial z dot z, and so on. So again, we basically just taken these equations and rewritten them in terms of here. But if you notice, this is our kinetic energy. This is our potential energy. We don't have to deal with what direction is this force going in, or how does it change as long as we go this curve. We just have to calculate energy, which is usually, okay, not usually, but oftentimes easier than calculating the forces. Okay. Now, I sort of fibbed earlier when I said that this is your Lagrangian. Technically, there can be more terms added on to that. Those extra terms are called constraints. What those constraints do is they would allow you to say, for example, give some curved wire, and you have a bead. Okay? So you have a bead on a wire. The bead has to follow the wire. So we know what form, like the trajectory has to draw out this path, but we don't know it as a function of time. You can add extra terms called constraints that would basically, one constraint would be like, for example, you're constrained to lie on this curve, or you're constrained to lie on the wire. Or another one would be like, you're constrained to be on the inside of a cone because like you're doing that demo where you roll a ball on a cone and it stays constant height even though there's gravity pulling it down. So that is an advantage of this formulation, is that just by adding those extra terms, this form does not change for calculating the equation of motion. However, you have to include extra forces, which are often very difficult to calculate. So, yeah. So, you guys remember from linear algebra, there was a concept of projections and change of basis? Well, that quantity, or that concept also holds true for functions. Specifically, we're gonna, well, when we were talking about f equals ma, we could also rewritten it as f is equal to p dot. And we really like momentum as opposed to velocity, so we want to look at this in a different way, in a lens that allows us to look at it from the point of view of momentum and position instead of velocity and position. To do that, we're going to do what's called a Legendre Transform. If I can spell it correctly. There's a rich mathematics behind how to do the Legendre Transform, which I wrote about in my notes, but I'm just gonna skip it. Oh, thank you. Basically, if you have two functions, f, or you have f, and it can be a function of x0, or x1, x2, it's a function of multiple variables, and we want to Legendre transform one variable to its conjugate variable. What we do is let's call the conjugate variable y over partial xi. So that's how you get the conjugate variable. The one that you want to transform, or to get the transform function, let's call that g. That's just going to be equal to xi, yi, and you sum over however many. So like if you want to do it for xi1, or x1, x3, and x7, then you would do x1 plus x1 y1 plus x3 y3 plus x7 y7. So you sum up over all the i's you're interested in, and then you just subtract f. Okay. Once you get this quantity, you then, using these statements, rewrite everything in terms of y. Then you have your Legendre transform. So let's try that with our Lagrangian. So it turns out that if you apply the Legendre transform on your Lagrangian, you will get this quantity I'm going to call H. Or first starting off, we have partial x dot. We're just going to call that P. Exercise, if you guys want to, you can show that this is the classical quantity we call momentum, or this is the quantity we call momentum. And again, this is a nice form because it generalizes, because plugging in theta dot gives us angular momentum, plugging in r dot gives us momentum along the radial direction for circular motion, or whatever coordinate function you want. Plugging that in here gives us the corresponding momentum. So, okay, this is a quantity we call the Hamiltonian. This is the general form of how to do it. 99% of the time, it will take the form of t plus v. It's when you have certain constraints on, or when you have specifically coordinates that are change as a function of time, this won't be true. Or you have some other wonky coordinates, this won't be true, but this will always be true. One thing, if you go through the math of Legendre transform, you find out that it's cyclic. So if I were to then try, or I guess a nice easy way to show that is I can rewrite this as Hamiltonian is a Legendre transform of the Lagrangian, but also the Lagrangian is a Legendre transform of the Hamiltonian. That means that q dot is going to be partial h over partial p. Okay? This equation will become important in a moment. But let's actually use this property of the Hamiltonian and plug it into this equation and see if we can figure out what the equation of motions are. So we have d over dt. We already said that this is our momentum right here. So d over dt of p is going to be equal to negative x. I'll just call it q. I sort of switched from using x's to q. It's just typically when you're doing Hamiltonians, q's are nice because Hamiltonians are easy to do in general coordinates. And this would just be this term, which we also said is this. So and if you go through the math, you find out that this just becomes separate. Double check. Yeah. So if you go through the math, you find out that this is true. So if you notice, we have q dot is equal to the partial derivative of the Hamiltonian with respect to momentum. We find that the momentum, or the time derivative of momentum, is partial derivative of the Hamiltonian with respect to position. So, and the negative of that. So it's really easy to drop this negative, so don't drop it. Okay. So now that we have this concept, we can talk about something called phase space. Phase space is basically a way of talking about the current we're talking about the current configuration of the system, although there is something called configuration space, which also does that. But basically, for the simple one-dimensional motion case, we put our position on the x-axis and our momentum on the y-axis. One point in phase space does not, or a point in phase space does not correspond to a point in real space, or like our normal positional space that we interact with every day. Instead, it corresponds to the position and momentum. So a point here specifies the system. Since from here, if we know the momentum, or we can get momentum, or how momentum changes from position, and we can get how position changes from momentum. So for most systems, that's all you need to characterize a system. That's equivalent, since we know going back to Newtonian methods that position or momentum is related to the first derivative of position. That's equivalent to saying that that to specify a system, you only need its position and the derivative of its position at one point in time. And we could have done a similar thing where we just put q dot in q for when we were in the Lagrangian, or when we were talking about Lagrangians. Problem with that is when you have second order differential equations, you can sometimes get issues where you can have like you can get I don't want to call them trajectories, because trajectories is typically what we call position as a function of time for particles, but you can get two paths in spaces in like q dot versus q, where they both would go through the same point, but then branch off. When we do that with momentum and position, that isn't an issue. That basically saying that you have a point, and then your Hamiltonian, when you apply those equations, gives you a trajectory, or a path in phase space. That this is unique and it's not going to intersect any other path. Yeah. Another useful thing about phase space is there's something called Liouville's theorem. Liouville's theorem, or I guess that's pretty good explain. Let's say I'm taking like an advanced lab class, and like most advanced labs, the department doesn't provide the best equipment, so there's a lot of uncertainty in in my measurements. So let's say I measure the particle having this position and this momentum, but I know the uncertainties, so realistically my particle is somewhere in this box in space, or that's square. As time evolves, Liouville's theorem states that this box, whatever shape it becomes, like as time goes on, it goes from that shape to this shape. Liouville's theorem guarantees that these shapes have the same area. So one way that this is useful is if I want to try and map out trajectories of particles, what I can do is I can start with 4 particles in phase. Because it's initial conditions, I can set them to be whatever I want. So I can set them out to form a nice square. If I let just a little bit of time pass, not a lot, maybe less than a second or something, then the 4 particles these 4 points in phase space will map to a new shape that won't be a square, but because it's such a short time, we can roughly assume it's a square. Yeah, there's no separate color. But because I know they're roughly a square, and I know that the areas have to be the same, I can use that to figure out, basically once I know 3 of them, I can just know where the 4th is, just because of Liouville's theorem, and assuming it's roughly a square. So the utility in that is, like, if it allows you to, it lets you know if you have bad equipment, because then you might find, instead of something being like that, you might find something like that. So you get that shape, and in which case you would know your equipment's really bad, or you made a mistake with this measurement. Another way that it's useful is it allows you to test allows you to test to see how valid your Hamiltonian is in describing your system. Because you can measure what these 4 points are and what these 4 points are, but then you can also use the Hamiltonian to figure out how these points should map and see how close each other are. Okay. So another nice thing with once we have our Hamiltonian is we can talk about Poisson brackets, because as we said before, there's an these two things are very close to being symmetric, but one has a negative sign and the other doesn't, so it makes it really hard, or very easy to get tripped up on that. So we have this operation called the Poisson bracket, which we denote with curly braces. The way Poisson brackets work is so Poisson braces are just defined to be this.
The last one is a Q.
Yes, my bad. Yeah, should be Q. So partial the first one with Q, partial the second one with P. You multiply the two quantities together, then you subtract partial the first one with P times the partial the second one with Q. If you plug in, and then if you actually go through the math and try like position with the Hamiltonian, you find that this just becomes negative partial H over partial Q, which is P. No. Q and H, you get positive partial H over partial P, which is Q dot. And then doing the same thing for P, you get P dot. So when we talk about Hamiltonians, P dot. So if we take the Hamiltonian as some quantity, or take the Poisson bracket as some quantity with the Hamiltonian, we get its time derivative. More specifically, we, or is it time derivative or the partial time derivative?
You get the time derivative without the partial.
Yeah. So, I mean, to be more specific, to get some quantity, which I'll call F, we actually need to take the Poisson bracket with the Hamiltonian, and then also add on a partial time derivative. If you guys have taken quantum mechanics, then you'll notice that this looks very similar. For any, and I don't watch this, for any operator, you have H bar. We have a corresponding equation. And this will not be the first time in this lecture that you see a connection between classical mechanics and quantum mechanics. But yeah, so I mean, there's a lot more of a connection between these two, but again, this is an introductory course, or introductory lecture, so I'm not really going to go that far. And so all I wanted to do with that. Yes, okay. So, so the next thing we're going to talk about are generating functions. So far, I've mentioned a few times now that we don't have to use Cartesian coordinates when talking about Hamiltonians. That we can use like polar coordinates or whatever arbitrary coordinates you want. Once you have a Hamiltonian one coordinate system, it's convenient to sometimes transform it into a different coordinate system and get the corresponding Hamiltonian for whatever reason. So the annoying thing is that not every change of variables will preserve Hamilton's equations. So we have to take extra care to make sure that we're changing variables in such a way that these equations are preserved. So to do that, we have these four partial derivatives relation. If we start with P and Q, or we start with H, our normal Hamiltonian as a function of P, or Q, P, and time. And we want to transform it to a new Hamiltonian K as a function of Q, P, and time in such a way that Q dot is equal to partial H over partial P, and P dot is equal to negative partial H, or sorry, K, because we're in terms of the new variables, over partial Q. One way, there are partial derivatives relations similar to Maxwell relations that you can do, or that you can derive to show, but if you can find a function, which I'm going to call G, such that this is true, we can find a function G such that this is true, then it immediately follows that P and Q, or lowercase p and q and uppercase p and q, satisfy those partial derivative relations such that these equations hold. This is called your generating function. There's a lot of very complex stuff you can do with this, but for our purposes, we're going to use it for two things. One is to get the new Hamiltonian, that's just old Hamiltonian, plus partial G over partial T. Okay? And the second part is, I'm going to talk about that right now. Okay? So what do I want to keep up? I want to keep, actually up. Okay. So, actually I wanted to keep this up. So, we're allowed to, if we can find a generating function, then we know that this is true. Or then we know our change of variables preserves Hamilton's equations. And actually even more specifically, we have that for a, I really should not have erased that yet. For a generating function of this form, we have that our position, or our momentum is partial G over partial Q, and that this is our original momentum, and our new position is, okay. Well, we can, as long as we can find a function so that this is satisfied, we can choose any variable. Specifically, it's often nice if we can choose variables that are constants of motion. What I mean is that their time derivatives are 0. So, another way of putting that is, if we can find the special ones, then this would be 0, and this would be 0. An easy way of making these zeros is by making k 0. Okay? So, what we want is, we would like a generating function that can give us, that will allow us to get a q and a p such that this is true. And I'm going to rewrite this special function as s. Okay? So, specifically, that is what we want. So, I probably should have done an example earlier, but let's do the harmonic oscillator for an example that this is true. Okay, so harmonic oscillator, we have for our t is 2. Okay. This is our Hamiltonian for the harmonic oscillator. And, oh, actually it should be, okay. This is the Hamiltonian for the harmonic oscillator. And we want to find a generating function S that gives us 0 as our new Hamiltonian. To do that, we start with this relation, and again, because this is a special generating function, we're going to call this S. We have that this is true. So we're going to plug this and this into our equation. I'm going to erase this. So we get so we are trying to solve this equation, and if we can do that, then we know we have a generating function, which means that we can change our variables from Q and P to two new variables which are constants in motion, or that will be constants in motion. So to do that, what we're going to do is, if you notice, this side is independent of, this doesn't depend on t, this doesn't depend on t. This is the only thing that depends on t, but nothing else depends on t, so we know that this must not, or that partial s over partial t must not depend on t. So we can call this some constant, which I'm just going to call it e, or negative e. Okay. Rearranging, we find that s is equal to some function of position minus et. Okay. If you plug this in, you find, if you take the time derivative, or time partial derivative, you see that all you get is e, which is independent of time, so that this equation is valid for all values of t. Okay? So now we plug that in, and then rearranging, we get this is true. You can do some calculus or basic differential equation work to get the answer. And the answer you get is, can you scroll to equation 68? Sorry, where is it? Sorry, 94, actually. You get that the equation for S is over omega So this is our solution for S from solving that differential equation. We know that this is a generating function, which will give us some constants of motion if we can choose the right things to take the partial derivatives of. Well, hold on a little bit. Okay. So in particular, that should be ET. We see a bunch of E's everywhere, so let's take the derivative with respect to E. This seems like it's a lot of hard work, but it ends up being really easy. Okay. And we, from what I just had here earlier, we know that E would be a constant of motion. Would it be a constant? Because if you look here, what is it? Because we know that partial S over partial T was equal to negative E, and the rest of the equation didn't have time in it, or it didn't explicitly have time in it, so we knew that E had to be a constant of time. There is a more rigorous argument to show that E is a constant of time. I'm just trying to do it very succinctly, but a potentially bad argument. Rearranging this, we find, or rearranging this, solving for Q, we get that Q is equal to root 2E over M omega Does this look familiar to you guys? You guys may have, usually this is written with the cosine instead of a sine, but this is the equation, or the solution to the harmonic oscillator. This process I went through to solve this is definitely not the fastest. The reason I wanted to show this is because the equation that I had up earlier, 0 is equal to h plus partial s over partial t, that's called the Hamilton-Jacobi Equation. That's really useful when trying to, what is it? It's really useful when looking in condensed matter, specifically, what is it? Like a lattice of atoms, and trying to look at normal modes of energy propagation. You would go through a process similar to what I just did, except to calculate much more complicated solutions, where this ends up being the most efficient way to do it. And yeah, that's really all I have.